Now that we've gone back and we've reviewed concepts of prime and irreducible and divisibility, we're ready to get in and start defining a unique factorization domain, or an affectionately called UFDs for short, to spare yourself that mouthful. So an integral domain D is a unique factorization domain if two things happen. First, if every non-zero non-unit of the domain can be written as a product of irreducible elements of the domain. And the second condition that we need is that this factorization into irreducibles is unique up to the order of the terms and up to multiplication by units. So let's explain a little bit what that means, and let's get some examples. So our first example, and really the best example, is the integers. The integers are a unique factorization domain, and truly, if you want to be looking at another domain that really has the exact same properties as the integers and is really the same in terms of an algebraist or a number theorist point of view, you want to be looking for something that's a UFD. Now, in terms of what do these two conditions mean for the integers, this is the fundamental theorem of arithmetic. If we take a number like 21, which is an element of the integers, we can factor this uniquely as a product of primes, and primes and irreducibles are the same in the integers, remember? So we can take 21 and we can write it as 3 times 7. And the uniqueness means this is the only way to write it as primes. Not really. I mean, we can write 21 as 3 times 7. We could write it as 7 times 3 if we wanted to. So those irreducible elements, those primes 3 and 7 and 3, we could change their order, and that's okay. The other thing is we could multiply by units. Now a number like -1 is a unit inside of the integers, so we could also write 21 as a product of 4 things. We could write it as -1 times -1 times 3 times 7, and that's okay, because we don't care about the two negative ones being there. The irreducibles that showed up, the 3 and the 7, and their multiplicities are unique. And so that is, those are the important things. Right? We don't care about the units and we don't care about the order. And the first part is saying there's nothing really special about 21. If we took any arbitrary non-zero non-unit, so any number other than 0, 1, or -1, we could write it uniquely as a product of primes inside the integers. A non-example is equally helpful. If we took D to be z adjoining the square root of -3, which was our example from the previous video, this is not a unique factorization domain, since the numbers 2 and the number 1 plus the square root of -3, those were both irreducible. That's something that we argued. And when we take the number 4, I can write it as 1 plus the square root of -3 times 1 minus the square root of -3. I could also write it as 2 times 2. All of these things are irreducible inside this domain, and 2 is not the same thing as 1 plus the square root of -3. They're not off by multiplication by a unit. Last but not least, if we take a field and we adjoin x to it, where x is an indeterminate, this happens to be a unique factorization domain. And it doesn't matter what the field is. It doesn't matter if it's the integers, it doesn't matter if it's complex numbers, it doesn't matter if it's z mod 5z. And this is actually something that's even a little bit, this is a special case of something that's a little bit more general that we'll discover as we work through the slides. Now the next thing that we want to define and get some examples of are Euclidean domains. Sometimes I think your textbook abbreviates Euclidean domain ED. I just call it a Euclidean domain because I don't feel like it's that long. But an integral domain D is called a Euclidean domain if there's a function little d called a measure on the domain. It maps the non-zero elements of the domain to the non-negative integers, and it has to satisfy 2 properties as well. So the first property is that d of a is less than or equal to d of a b, where a and b are non-zero. And the second thing is we basically need to have the quotient remainder theorem here. So if a and b are elements of the domain, if the element b is non-zero, then we can write a as q times b plus r, right, for where q and r are elements of our domain. And it either has to be the case that r is 0, in which case we don't define the measure on that element, or else the measure of the element r has to be strictly less than the measure of the element b. We're calling it, I'm saying d is a measure, but you could also say d is sort of like a distance function. And here are some examples here. The integers happen to be a Euclidean domain, where d is the absolute value function. Similarly, if we take a field f and we adjoin an indeterminate x to it and we look at the polynomial ring f adjoined x, this is a Euclidean domain. And what's our measure? Our measure is the degree of the polynomial. And our last example here is the Gaussian integers. These happen to be a Euclidean domain. And here the measure happens to be the norm function that we discovered earlier. The norm of a plus bi is a squared plus b squared. If this is a measure function or a distance function. If you think about the complex plane, you can think about these Gaussian integers as the lattice points inside the complex plane. And what you're taking here, this a squared plus b squared, you're taking the distance from the point in the complex plane to the origin. Now, once we've discussed PIDs, principal ideal domains, before. I've just introduced two new definitions, UFDs and Euclidean domains. I want to know what's the hierarchy among these domains. Are they all the same? Are they different? Does one imply the other? And there's a very strict and nice hierarchy or collection of relationships between these three things. The first theorem that we're going to talk about, and we'll go through the proof of this, is that if you have a Euclidean domain, then this is automatically a principal ideal domain. And the theorem we'll discuss after that, although we won't prove it in full detail, is that if we start with an integral domain that's a principal ideal domain, then it's also a unique factorization domain. So if you recall from, I think this was two presentations ago, chapter 16 of Galilean, when you take a field and you adjoin an indeterminate to it, when you look at f adjoined x, you get a PID. And so the fact that f adjoined x is a UFD is a special case of this theorem. When you're looking at a principal ideal domain, you automatically have a unique factorization domain. So this is what I meant when I said f adjoined x being a UFD is really a special case of something. It's a special case of this theorem. Now, something that's interesting is that all of these relationships are strict. So Euclidean domains are not secretly the same as principal ideal domains, and principal ideal domains are not secretly the same as unique factorization domains. That is, each of these containments is a strict containment, and these separate classifications are really necessary. So when you look at z adjoin x, this is an example of something that's a UFD that is not a PID. I've hinted at this before, and proving this is not very hard. This is something that you're capable of doing with just the tools that you have if you wanted to prove it very rigorously. The next example is something that would be pretty difficult to prove, would be beyond the scope of this class, really, for now. That is when we take z adjoin gamma, where gamma is a root of the irreducible polynomial x squared minus x plus 5. This is an example of something that's a PID that is not a Euclidean domain. It's also another good example because we saw when we were looking at the Gaussian integers, z adjoined I, that norm map that we defined earlier on happens to be a measure for that space, z adjoined I. However, if we had a measure, if that norm map was always a measure for z adjoined gamma, no matter what gamma was, then whenever we looked at z adjoined gamma, we'd be looking at a Euclidean domain. And here I'm stating that z adjoined gamma is not a Euclidean domain. So what that means is that norm map that we defined earlier for z adjoined gamma, no matter what gamma was when it was a root of something of this form, it doesn't always turn out that norm map is a measure on the space, which is kind of interesting. And right now I think I'd like to do the proof, since it's somewhat short, that a Euclidean domain that happens to be a Euclidean domain is automatically a principal ideal domain. And this should look really familiar. And we're going to go through the proof, and this should seem like a very familiar concept to you. So here's our theorem. If we have a Euclidean domain, then it's automatically a principal ideal domain. So let's begin. Let's let little d be our distance function, or our measure, that exists on our domain D. And let's take I, which is a non-zero ideal. What we need to do is show that it's equal to the ideal generated by something. So what we're going to do is we're going to start by picking an arbitrary non-zero element within the ideal. And we don't really want anything arbitrary. We want it to be non-zero, but let's fix one that has d of b minimal. Now let's take another arbitrary element of the ideal, and since we have this measure function, the second property of a measure function is whenever we have a non-zero element, we can take any old element in the world and we can write it as QB plus R, where two specific things happen. The Q and the R are elements of the domain, and either that R is 0 or the measure of the element R is strictly less than the measure of the element B. However, in this latter situation, if we were to run into this, D of R is less than D of B, then we would have contradicted our choice of the element B. We've selected B with the property that D of B is minimal. So there can't be anything else inside this ideal that has a smaller measure. And so we can't be in the latter situation. That means we have to be in the former situation. And so we must have it be the case that A is actually just Q times B. We must have R equal to 0 in this decomposition, and A must be Q times B. This shows that the element A belongs to the ideal generated by B, and A was an arbitrary element of the ideal, so we have this containment. The ideal I is contained in the ideal generated by B. However, we picked B to be an element of the ideal I, and so we have the other containment in an obvious way. We have that the ideal generated by B is contained in I, and we gain equality from this. So we see that I is the ideal generated by B, where B is something with minimal measure inside of the ideal, and this shows that D is a PID. Now, when I say this should look really familiar to you, what I mean is that this proof is very similar to actually two proofs that we did when we were working through the slides of chapter 16. So I think I showed you that the integers were a principal ideal domain in those sets of slides, and I also showed you that f adjoined x was a PID in those sets of slides. And all I did is I repeated this proof twice when I did those slides. In the first case, I used my absolute value measure to show that the integers were a PID, and in the second case, I used my degree function. Take a polynomial and look at its degree. That was our distance function there. And I've just made this same argument with specific distance functions. So if we just take a domain and have a more arbitrary distance function, then that proof generalizes to the proof we have here.